Hello there, this is a geometry video. It is chapter 8, section 4, and today we're going to be discussing trigonometry, one of my favorite topics in geometry. And the word trigonometry, if you want to know where it comes from two Greek words. The first is trigon, which means triangle, and the second is metron, which means measures. So basically the study of trigonometry involves triangle measurement. And so today we're going to be talking about trigonometric ratios. And a trigonometric ratio is the ratio of the lengths of two sides of a right triangle. All right, and we're going to talk about that. And what you see on the board there, we're going to explain a little bit further. I want to remind you that by the angle-angle similarity postulate that we had earlier in the year, a right triangle that has a given acute angle measure is going to be similar to every other right triangle with the same acute angle measure. So basically, trig ratios are constant for any given angle measure. So based on that, we have these trigonometric ratios. And so we have these three ratios. The first is the sine ratio, cosine ratio, and the tangent ratio. Now again, we're talking about right triangles here, so this only applies if you have a right triangle. And you can find these ratios. I'm going to fill in my information over on the other side. But before we get to all that, we have to have some anatomy of the right triangle again, just to review, because you have to have that down pat if you're going to get these ratios right. So what I've done is I've got two triangles here, because every right triangle is going to have three parts: an adjacent side, an opposite side, and a hypotenuse. In the past we've talked about long leg, short leg, but now we're going to be using words like adjacent and opposite. And the ADJ that you see here represent adjacent, the OPP is for opposite, and the HYP is for hypotenuse. Now the problem is that the same side of any given triangle won't always be the adjacent side. So for example, if I give you a diagram and I call this the adjacent side, AC the adjacent side, and if you think that it's always going to be the adjacent side, you're going to have a hard time. Because as you can see in the second diagram, it's not the adjacent side, it's the opposite side. So basically these terms, adjacent and opposite, refer to the angles that they're coming from. So the first diagram, what I've done is I've highlighted the angle A, because we're talking about the adjacent and the opposite sides based on angle A. In part B, we're talking about the adjacent and opposite sides of the triangle based on angle B, which is why the B is highlighted. And so basically, when you're talking about angle A, the opposite side in the diagram to angle A is BC, segment BC. But the adjacent side to angle A is AC. And of course the hypotenuse is always going to be the same because it's always opposite the 90-degree angle. So in the second diagram, I'm basing it off of angle B. So in this case, because angle B is down here, the opposite side is not BC like it was in the first diagram. The opposite side is AC when you're referring to angle B. And then the adjacent side is going to be BC when you're referring to angle B. So basically opposite is going to be the opposite side of the angle that you're looking for. The angle metric can have different names, so just have to be careful that you always look for opposite. And adjacent means that it's basically touching the angle. So you can see here that the point A and the point C don't touch angle B at all. But in the case of the adjacent side, it's touching right here at angle at point B. That's one way that you can help yourself remember. So then what we have over here is an acronym. I've written in different color the S, the C, and the T to separate the three different ratios. But basically what we do with this is we call this SOHCAHTOA. And the SOHCAHTOA is to help you remember that sine, the ratio for sine, is always opposite over hypotenuse. So SO is opposite over hypotenuse. Ka is adjacent over hypotenuse. The ratio is always adjacent over hypotenuse. And then for tangent, it's always opposite over adjacent. So SOHCAHTOA. It's important that you pronounce it correctly, because if you pronounce it SAHCOTOA, then you might think it's adjacent hypotenuse instead of SOHCAHTOA. So you're going to sound like you're part of an Indian tribe with SOHCAHTOA, but it's okay. So what I'm going to do over here now is for sine of A, because based on our acronym over there, sine of A is opposite over hypotenuse. So I'm going to write over here sine of A. The opposite side for A is side BC, so we're going to put BC over the hypotenuse, which is AB. In this case, for cosine A, I'm going to get adjacent, which is AC, over the hypotenuse, which is AB. And then lastly, for tangent of A, I'm going to do opposite, which is BC, over the adjacent, which is AC. All right? So that's basically filling in those trig ratios. For B, you'll see that I'm going to get different scenarios over here. For the angle B, sine is going to be the opposite is AC over the hypotenuse AB. So you can tell right now that the sine of B, the AC over AB, this ratio is the same as the ratio of cosine for A, AC over AB. Interesting, huh? Cosine B is going to be adjacent, so BC over hypotenuse, which is AB. And then our last one, tangent B, is going to be opposite, which is AC, over adjacent, which is BC. All right? So just like that, you can determine what the ratios are. That's what we're going to do in our first example up next. It says express each ratio as a fraction and as a decimal to the nearest hundredth. All right? So what we're going to do here is we have a right triangle. We have all of the sides measured. But again, it depends on which angle we're using as far as what the opposite and adjacent sides are. The hypotenuse is clearly always going to be QP because it's opposite the angle R, which is the right angle. So in part A, it wants sine of P. So sine of P means that I have to go to the vertex P, which is right here, and I have to use SOHCAHTOA. So sine is the SO part, that means OH. So opposite is going to be 15, and the hypotenuse is going to be 17. So sine of P is 15 over 17. And as a decimal, 15 over 17 is roughly 0. And it wants to the nearest hundredth, so it's 0.88. 0.88. All right. For part B, it wants cosine of P, so the same angle, but cosine is ca, so it's adjacent over hypotenuse. So that this is going to be side 8 over the hypotenuse 17, and as a decimal, that's going to be approximately 0.47. Okay, so not very complicated to do this. Tangent of P, again using the same vertex P. This time tangent is TOA, so it's opposite over adjacent. So opposite is 15. Adjacent is 8. And then our decimal is going to be 15 divided by 8 is going to come to 1.88 because it's 1.875. So to the nearest hundredth, it's going to be 1.88. So then we do the exact same thing, only this time we're going to be doing Q. So now we've switched from P's to, for D, E, and F, we're going to go with angle Q. So here's my angle Q this time. And for the sine, remember that's opposite over hypotenuse. This one's going to be opposite, is going to be 8. So we're going to get 8 over 17. Which is the same thing as cosine of P, if you'll notice that. Same ratio, so we're going to get 0.47. And then for cosine of Q, that's adjacent, which is 15 over the hypotenuse. So we get 15 over 17, which is the same as the sine of P, so we're going to get 0.88. And then lastly, we're going to get tangent of Q, which is opposite over adjacent. So the opposite side for Q is going to be 8. The adjacent side is going to be 15. So 8 over 15 is going to give us approximately 0.53 to the nearest 53333 repeating, but because they want us to run to the nearest hundredth, it's going to be 0.53. And that's basically how complicated it is to find ratios, trig ratios. It's not very hard at all. So now we're going to have you do the same thing here. There are 6 parts. You want sine, cosine, and tangent for angle J, and sine, cosine, and tangent for angle K. And again, you want to express it as a fraction and also as a decimal to the nearest hundredth. In example 2, we're going to use what we've learned in the past, a special right triangle to express the tangent of 30 degrees as a fraction and as a decimal to the nearest hundredth. So this might seem kind of complicated to you, but the easiest way to do this is to actually just make a triangle that we can visualize. So I'm going to do that here for you. I'm going to make myself a 30, 60, 90 triangle. And I'm going to go ahead and put in my 30 and my 60. So remember that the 30-degree angle is always opposite the shorter side. So based on our previous lesson, I'm pretty sure it was our previous lesson. Yep. We know that the ratio or the lengths of a 30, 60, 90 are going to be x, 2x, and x root 3. All right. Of course, you could have a different variable, but basically you're going to have a side length, twice that length, and then that length times a root 3 over here. So we don't know what the actual lengths are, but we want to express the tangent of 30 degrees as a fraction. So the tangent of 30 degrees, that would be this angle here. So we want to go, tangent is TOA, so it's going to be opposite over adjacent. So the opposite side is x. And the adjacent side is going to be x root 3. Like that. So for tangent of 30 degrees, we're going to take the opposite side, which is x, and the adjacent side, which is x root 3, and then simplify that. So it turns out that because the x on top and x on the bottom will cancel, you end up with 1 over root 3. But of course, it's improper to have a radical on the bottom of a fraction. So to get rid of it, we multiply both top and bottom by root 3. And what that gives us is 1 times root 3 is root 3. And on the bottom, you get root 9. But the square root of 9 is 3. So you get root 3 over 3. So the tangent of 30 degrees is equal to root 3 over 3. And that's the part that it asked us to express it as a fraction. So we've done that. And as a decimal, we can use the calculator and put root 3 divided by 3. And we get approximately 0.58. It's 0.577, so we're going to round to the nearest hundredth, and we're going to get 0.58 for our ratio. So now we're going to have you do the same thing, only this time you're going to be using the 45, 45, 90. Again, it'll help if you draw out the diagram and then use the formulas from our previous lesson to label the sides. All right, so now we're going to go to example 3, where we're going to be applying some of what we have here to finding missing lengths in a triangle. It says a certain part of a hiking trail slopes upward at about a 5-degree angle. So that's kind of what I've indicated here with this angle measure here, 5 degrees. After traveling a horizontal distance of 100 feet, so you have 100 feet here, along this part of the trail, what would be the change in a hiker's vertical position? So basically I want to know if the slope is at 5 feet of angle elevation there, and if I'm walking, this distance is 100 feet, that's the horizontal distance of 100 feet, then what was my change in vertical position? They want me to find out what x is here. And then of course it says what distance has the hiker traveled along the path. So if you're not talking about horizontal distance, they're asking what is this total distance here. So they want us to find y. So we're going to use our trig ratios to help us out. And so the first thing I'm going to do is I have the adjacent side, and I have, if you base it off of the 5-degree angle, the opposite side is x, and the hypotenuse is y. Since you don't actually have the hypotenuse, if you try to do the sine of 5 degrees, okay, remember that's where the angle measure goes. Sine A means A is the angle measure. So in this case, the angle measure is 5 degrees. So sine of 5 degrees is equal to opposite over hypotenuse, and you're going to get x over y. And there's too many variables. You have 2 variables in that case. You could do cosine of 5 degrees. And if you do cosine of 5 degrees, you're going to get adjacent, which is the 100, over hypotenuse, which is y. See, now in this case, you have only one variable, and that's what you're trying to find. So you don't want to use the sine function because it gives you too many variables. But you can use the cosine function, and then of course, you could also try the tangent function. The tangent function is opposite, which is x, over adjacent, which is 100. Okay? So you could use either one of these functions, cosine or tangent, will give you the answers that you're looking for. Now, in the case of tangent, we're going to find out what the x value is, and in the case of cosine, we'll find out what the y value is. So we're going to do both of those. So let's go with the tangent first. We'll multiply both sides by 100, and then the hundreds will cancel, and you'll get that x is equal to 100 times the tangent of 5 degrees. Well, we don't know what the tangent of 5 degrees is, and that's what you're going to need to use your calculator for. I'll tell you right now that when you do this on the calculator, it's very important that the mode of your calculator is in degree mode. So there is a mode button on your calculator right next to the second button, and when you look at that screen, you'll have normal, science, engineering across the top, but the third line says radian, and then it says right next to it degree. If your calculator says radian, if it's darkened, you need to use your cursors and go over to degree mode and put your calculator in degree mode. It is very important that you be in the right mode when you are trying to do these kinds of problems. All right, so now that you're all in degree mode, I hope, we're going to go to the calculator and get our final answer, our approximate answer. The exact answer is 100 tangent 5 degrees. So we're going to go 100 and then hit the multiplication button, and then you're going to hit the tangent button, which is of course across here next to the caret key. And then when you hit the tangent button, automatically a parenthesis will open. And so we're going to put in a 5, close that parenthesis. And it says it's approximately 8. They want us to, they didn't say what they want us to round it to, but we're going to stay consistent and go to the nearest hundredth, so 8.75. Excuse me. So the hiker's vertical position is 8.75 feet. All right, so 8.75 feet. And then we want to find the distance traveled here. So for that, we're going to use cosine. This time, we're going to go times y, and you're going to get y times cosine of 5 degrees equals 100. But this time, unlike the previous one where timesing by 100 pretty much just isolated the x by itself right away, This time we don't have the y by itself because it's y times cosine 5 degrees. So now we have to divide by cosine of 5 degrees on both sides. And now the y is by itself, and the exact answer is 100 divided by cosine 5 degrees. But we need you to put that in the calculator. So we're going to go 100 divided by cosine, and then the parenthesis opens up, we put a 5 in there, and then we close that, and you get 100.38 feet. So the horizontal distance was 100 feet, but the actual distance was 100.38, slightly longer because of that angle of elevation there. So that is how you find missing parts of a right triangle using your trig ratios. So now we're going to have you try these 3 scenarios, and we're trying to find the x. And then we're going to go to example 4. In example 4 is going to be different from example 3 in that the angle measure was given in the previous example. We knew that the angle measure was 5, and so you were only trying to find missing side lengths. But now you're actually going to be looking for the angle measure. It says use a calculator to find the measure of angle A to the nearest 10. So I don't need to know what the side length is. I want to know what the angle measure is. Now again, one of the first things you have to be able to do is to identify which trig ratio you're going to use in order to find this missing angle measure. And so you can set up the different options. It's all based on what pieces you have. So I want angle A, and I am given the opposite side, and I'm given the hypotenuse. So it doesn't make sense for me to try any ratio that involves the adjacent side because I don't know what the adjacent side is. Now, if I really wanted to make things harder for myself, I could use Pythagorean Theorem to figure out the third side, but that would just be more work. When I could just as easily use the opposite side and the hypotenuse would be sine. So it makes sense in this case to use the sine function. So sine of A is equal to the opposite side, which is 18, divided by the hypotenuse side, which is 27. Okay, but what I'm trying to find now is A. What is the value of A? And how do I get rid of A? And that's where you have to start using the inverse functions. Okay, and so it's very important that you know what an inverse function is. An inverse function cancels out the regular function. So the inverse function looks like this. Sine inverse. It has the same letter sine, but there's a little -1 here. This is not the same thing as 1 over sine. It's not the reciprocal, it's the inverse function. So sine inverse of sine A. So I take the inverse of the left and the inverse of the right. And this is kind of strange, but this is how you do it. So sine inverse of the left, sine inverse of the right. What happens on the left is that inverse functions always cancel each other out. So the sine inverse and the sine will cancel, leaving you with just A. But it doesn't cancel on the right. So this is where it becomes very important for you to use the right keystrokes in your calculator. When you go to the sine button on your calculator, right above it, you'll see the symbol sine inverse. So you need to make sure that you hit the second button first, then the sine button, and then your calculator will show up sine inverse with an open parenthesis. We'll type in 18 divided by 27, close that parenthesis, hit enter, and then it says 41.81. Now in this case it says to find the measure of angle A to the nearest 10th, so we want to take off the point, the 81 there, and just leave it as 41.8. This would be our angle measure. So that is how you do inverse functions. So now we'll let you try do yourself number 4 here. And then we have one last example. It says solve the right triangle. Round side measures to the nearest 10th and angle measures to the nearest degree. So they don't want any decimals for the angle measures. So we can use Pythagorean Theorem to find x, y. So we can say 5 squared plus 9 squared equals xy squared. That's the hypotenuse there. 5 squared is 25, 9 squared is 81. And so 25 plus 81 is going to give us 106. And then we can take the square root of both sides, and the square root of 106 is, we're going to round to the nearest tenth because it's a side measure. So xy is equal to 10.3 because it's 10.29, but we round to the nearest tenth, so it's going to be 10.3 for side xy. And then we want to find, when it says to solve the right triangle, it wants you to solve all the missing parts. So we found the missing side, but now you need to figure out what the two missing angles are. So now we're going to do that. And so to find angle X, we can use that the opposite side is 9 and the adjacent side is 5. So when you have opposite and adjacent, then you want to use tangent. So tangent of X is equal to the opposite side, which is 9, over the adjacent side, which is 5. So to find X, I'm going to do tangent inverse of tangent X equals tangent inverse of 9/5. So again, the tangent and the tangent inverse will cancel, giving me the X value. And we're going to round it to the nearest degree, so I'm going to go second tangent, so I can give a tangent inverse. 9 divided by 5, close those parentheses, and I'm going to get 60.94, but I'm going to round it to the nearest degree, which would be 61 degrees. Then to find angle Y, you can use the fact that all three angles of the triangle have to add up to 180, so we can say that 90 plus 61 plus angle Y should equal 180. So basically 180 minus the 90 minus the 61, your angle Y will equal approximately 29 degrees. So now we've solved the triangle. We found the two missing angle measures, and we also have the missing side length. And so now we have it all figured out, and that's how you solve the right triangle. So now we want you to try this last do-it-yourself question, and once you have completed this question, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.